Assalamu alaikum. Hope you are doing fine. The space around a magnet in which another magnet experiences a force is referred as magnetic field. And this magnetic field have magnetic field lines. The number of magnetic field lines crossing per unit area is referred as magnetic flux. In this video, we are going to learn about magnetic flux. Let me write the definition of magnetic flux on board. The number of magnetic field lines crossing per unit area is referred as magnetic flux, as I told you earlier. This magnetic flux is usually represented by letter phi b. Here, this symbol is read as phi, a Greek letter. Now let me show this to you with the help of a simple diagram. Suppose this one is a uniform magnetic field. When the magnetic field lines are parallel, then we call such a magnetic field as a uniform magnetic field. And in such a magnetic field, the direction and magnitude remain same throughout. Now, in one such a magnetic field, if I place a plane area in this manner, the number of magnetic field lines crossing per unit area of this surface is referred as magnetic flux. Here, the arrow mark represents the direction of magnetic field, denoted by letter B vector, and here a normal means a perpendicular line. This is the normal. This normal provides the direction of area. This is area vector, A vector. Okay. Now mathematically we can represent magnetic flux as this way, phi b. Mathematically it can be represented as B vector dot A vector. Now, when vectors are taken in product in this way, we call it as a dot product. When you come across two vectors in a dot product, suppose I write A vector dot B vector. This is a dot vector of two vectors. Then this can be written as AB cos theta. Here, theta is the angle between A and B. Similarly, if we come across two vectors in a cross product, then it can be expanded as AB sin theta. Okay. By following this, I can write phi b as BA cos theta using this. Now, for convenience, I box this expression. this manner. Now this is how mathematically we can represent magnetic flux in this way. Now I go ahead. I am going to discuss the few special cases. So for that I draw uniform magnetic field. In this manner. I draw one more line. Then, to discuss a special case, I take a plane surface. Which appears something like this, making an angle of 90 degree with the magnetic field. Here, the direction of a magnetic field is represented by this arrow mark, B vector. Then the area vector is represented by this. Okay, I use a different color. By this perpendicular line to the plane surface. This is the area vector. Okay. Now, if you compare the angle, if you find the angle between B vector and A vector, you may find it is nothing but 0 degree. Clear? Then the first case. Now, special cases. The first case, case 1. In case 1, we take a theta equals to 0 degree. If it is so, then cos of theta is equal to cos of 0, which is nothing but 1. Cos of 0 is 1. Clear? Then I am going to substitute the value of cos theta in this expression to get the value of 5b. So what do I get? I get this. So 5b equals to BA cos of theta. The theta value is 0. So cos of 0. Cos of 0 is 1. Right? BA multiplied with the value is 1. So it is nothing but BA. So when theta is taken as 0, 5b becomes BA. We get the maximum value for magnetic flux when the plane surface is placed perpendicular to the magnetic field. Now, in another case, what I do, I take the magnetic field, the surface is placed parallel to the magnetic field. Let's see. Now, this line normal represents the area vector. Now, the angle between magnetic field and the area vector is 90 degree here. In this case, it is 90 degree. I take this one as case 2. In case 2, theta is taken as 90 degree. So, cos of theta is taken as cos of 90 degree, and cos of 90 degree is nothing but 0. That I am going to mention here in this equation. So phi b equals to BA cos of 90 degree. Okay. The cos of 90 degree is 0. So what do I get? I get this. BA multiplied with 0. What do you obtain? 0. Here, phi b is the minimum or is 0 when the surface is kept parallel to the magnetic field. Right? Next, what is the unit of magnetic flux? Magnetic flux is measured in Weber. The unit of magnetic flux is nothing but Weber. And the short form of Weber is WB. Clear? And there is one more unit. In a CGS system, magnetic flux is measured in Maxwell. Root of phi b in a CGS system. This is a Maxwell. Here, 1 Weber. Now I am going to relate the Maxwell with the Weber. Here 1 Weber is equal to 10 power 8 Maxwell. You remember this? Now go ahead. Now I am going to show you how to get the dimension of magnetic flux. Dimension of magnetic flux. Dimension of magnetic flux. Now, we know the force acting on a current carrying conductor placed in a magnetic field is represented by this expression. F is equal to BIL. Here, F stands for the force acting on a current carrying conductor of length L placed in magnetic field of value B. So from this, B equals to F upon IL. Here, it is obtained after cross multiplication. Here I have taken IL towards this side. So it divide here. So B equals to F upon IL. Now let's go ahead and see. So it is so. Then we know force is the product of mass and acceleration. Mass and acceleration. And here acceleration is nothing but rate of change of velocity. Velocity divided by time is acceleration. And velocity is displacement by time. So by keeping this in mind, if I substitute this one here, what I get? Acceleration is equal to S divided by T upon T. So is equal to displacement divided by the square of time. This is the expression for acceleration. Now I am going to use all those things here. So this can be written as B equals to mass into acceleration. Acceleration is written in terms of displacement and time. So S upon T square divided by current multiplied with the L. Okay. So this is the, I have written B in terms of all these things. So this will help me to get the dimension of magnetic flux. Clear? Now, what is magnetic flux? What is the expression for magnetic flux? It is 5B is equal to B A. If the angle is 0 degree. Okay, I take it in this manner. Now we have the expression for B, that is M multiplied with S upon T square divided by I into L. Then here A is area. Area is nothing but, what is area? Area is length into breadth. Fine. All the things we have here, L and L get cancelled. What remains is this. M. No, this can be as M multiplied with S. The T square can be taken to denominator. I T square. And here B is left here. Okay, B stands for breadth. Now, the dimension of 5B. Dimension of 5B. Okay, here the dimension of mass is M. The dimension of what is this? Yes, this is nothing but displacement. Dimension of displacement is L. Okay, then B is also breadth. Its dimension is again L divided by the dimension of current is A. A stands for ampere. Remember this. Then T stands for time. So the dimension is T square. Dimension of time is T. Here we have square, so it is squared. Now this can be written as, let's see, divide it carefully. Here we have L twice, so it becomes L square. So this is written as M as such L square. Then here it's ampere. No, it is there in denominator. When it is taken to numerator, we get this. First, I take this term. T power 2 becomes T power minus 2 when taken to numerator. Then A will become A power minus 1. This is the dimension of magnetic flux. I have taken more time, but you might have understood. Then one thing I would like to mention here. When we talk about quantities, there are two types of quantities. One is a scalar quantity, another one is a vector quantity. Here, magnetic flux is nothing but a scalar quantity. It is a scalar quantity. What is meant by scalar quantity? Scalar quantity is one which has got only a magnitude and no direction. What do you mean by magnitude? When I say magnitude, it means size or number, or even you can say quantity. Okay, magnitude means size, or in simple words we can call it as number 1, 2, 3, something like that. Okay, let me explain this with the help of a simple example. Why do I say that? It has got only magnitude and no direction. Here I take one area, a different color. This area I take. I take one area, plane surface. If you look at this plane surface, you may find this plane surface. Through this plane surface, 1, 2, 3, 4. 4 magnetic field lines are crossing through this plane surface. So, the magnetic flux in this case is 5B equals to 4 Weber. Say, I represent the magnetic flux by number. Do not have any direction. Remember this. Now I take another surface. This one. This surface is little small. The area of the surface is little small compared to the first surface. Here, you see, only 1, 2. 2 magnetic field lines are crossing through this area. So here, in this case, the magnetic flux 5B is nothing but 2 Weber. Here is 4 Weber, here it is 2 Weber. So again, the value, it is not only a number without any direction. Clear? So it is a scalar quantity. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.